Welcome to our Engineers Newsletter Live program on high-performance VAV systems. I'm Jeannie Harshaw from Trane System Engineering Group, and I'll be your host as we examine VAV system design and control strategies that can significantly reduce energy use for high-performance buildings. This course is approved by the U.S. Green Building Council for 1.5 GBCI continuing education hours for the LEED Credential Maintenance Program. After attending today's program, LEED professionals may submit their hours to Green Building Certification Institute. Today's program is also registered with the AIA CES education system and qualifies for Health, Safety and Welfare and Sustainable Design credit. So AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, please check your state's rules to see if credit for attending can be applied to your engineer's continuing education requirements. If you have questions regarding content covered today, please fax them to the number on the screen or send us an email at enl@trane.com. Remember to include your email address so we can get back to you. Answers to all questions will also be available in a few weeks, so be sure to follow up with your Trane sales office for a copy. Some of the information today will look familiar to many of you. That's because we've covered it in various forms throughout the years. However, today we're focusing on strategies you'll find in high-performance VAV systems. We'll start out with an overview of the ASHRAE Standard 189.1 requirements for VAV systems. Then move into various strategies for making a VAV system high performance, like optimized control strategies, cold air, energy recovery, and others. And finally, we'll share energy modeling results comparing high performance VAV systems to other systems. To cover this information today, we have two faces most of you will recognize. Dennis Stanke, a Trane Staff Applications Engineer, ASHRAE Fellow, and current chairman for the ASHRAE committee responsible for Standard 189.1, and John Murphy, also a Trane Applications Engineer. Now I know we're here to discuss VAV systems, but since high-performance VAV systems often fit best in high-performance green buildings, it seems appropriate to start with Dennis summarizing the requirements found in ASHRAE 189.1, the high-performance green building design standard. Dennis?
This standard covers the same buildings as 90.1, the energy standard, but its provisions go way beyond energy. Here are some example provisions. Sites must be selected and designed to reduce environmental impacts such as urban heat island effect and rainwater runoff. Water use must be reduced by planting less turf grass, using more efficient water fixtures, recovering HVAC condensate, and not using once-through HVAC systems. Buildings and systems must reduce energy use compared to 90.1, and they must include site renewable energy. To assure high indoor environmental quality, buildings must meet all 62.1 ventilation requirements, plus sense outdoor airflow, and they must comply with standard 55 comfort requirements and some basic acoustic requirements. To help protect the environment and the atmosphere, buildings must be designed to reduce construction waste and to increase use of local materials, and no CFCs are allowed. Finally, to help assure that they work as designed, high-performance green buildings must be commissioned, and plans for erosion control and moisture control during construction must be written and followed. In addition, plans for operation, maintenance, service life, and so on must be written and retained by the owner. How does Standard 189.1 relate to high-performance VAV systems? Well, since the standard is based on compliance with the energy standard, high-performance VAV systems must use at least those VAV controls required by 90.1. We'll cover some of these in detail today. If a project uses cold air distribution, then energy modeling using the performance option in 189 can show considerable reduction in energy use for the proposed building. So we'll talk about that. Finally, high-performance green buildings must use energy recovery more often than systems that merely comply with 90.1. So high-performance VAV systems need additional energy recovery too. Here's a quick comparison of some of the 189 energy requirements compared to the corresponding 90.1 2010 requirements. For optimal start and fan pressure optimization, the requirements in 90.1 2007 are the same for 189 and the newest version of 90.1. Like 90.1 2007, 189 doesn't require supply air temperature reset, but 90.1 2010 does. That makes it more stringent than 189 in this respect. Zone level demand controlled ventilation is required in zones with more than 40 people per 1,000 square feet by both versions of 90.1, but 189 requires it in any space with 25 or more people per 1,000 square feet. So the green building standard is more stringent in this case. System level ventilation reset control is not required by 189, but it is required by 90.1 2010. So here again, the energy standard is more stringent than the green building standard, at least for now. None of these standards require cold air distribution, but you could use it and show significant energy savings if you use the performance option in standard 189. To comply with 189, air-to-air energy recovery must be more effective, and it must be used in more buildings in more climates than the 2010 version of the energy standard. In this small sample of energy requirements, you can see that sometimes 189.1 is more stringent and sometimes 90.1 2010 is more stringent. As chairman of the standard 189.1 committee, I can assure you that work is underway to make the energy requirements in the next version of 189 equal to or more stringent than those in the 2010 version of 90.1.
The first key ingredient to make a VAV system truly high performance is the use of optimized system control strategies.
We'll discuss a few of these strategies today, starting with optimal start. In many applications, a simple time clock or time-of-day schedule is used to start and stop the HVAC system. During the unoccupied hours, the system is shut off and the temperature is allowed to drift away from the occupied set point. The time at which the system starts in the morning is typically set to ensure that the indoor temperature reaches the desired occupied set point on either the coldest or the warmest morning of the year. The result is, for most days, the system starts much earlier than it needs to. This approach increases the number of system operating hours and energy use. An alternative is to use a strategy called optimal start. A building automation system is used to determine the length of time required to bring these zones up to from their current temperatures up to the occupied set point temperature. Then it waits as long as possible before starting the system so that the zones reach the occupied set point just in time for occupancy. This strategy saves energy by not starting the system earlier than necessary and ensures comfort by not starting the system too late. A similar strategy is optimal stop. As I mentioned, at the end of the occupied period, the system is shut off and the temperature is allowed to drift. However, the building occupants may not mind if the zone temperature drifts just a few degrees before they leave for the day. Optimal stop uses the same automation system to determine how early the heating and cooling can be shut off for a zone to allow the temperature to drift just a couple of degrees from the occupied set point. The supply fan continues to operate and the outdoor air damper remains open to continue ventilating the building. Only cooling and heating are shut off. This strategy saves energy by allowing the indoor temperature to drift early. Now, the green region indicates a scheduled occupied period. This is the time span that the building operator has identified that this building is normally expected to be occupied. Since building operators want to avoid complaints from the occupants, they often take a very conservative approach, stretching this occupied period from very early, just in case someone comes in early, to very late for those who occasionally need to work late. This can be costly from an energy perspective. So here's a few simple solutions that can minimize comfort complaints and avoid wasting energy. First, use aggressive rather than conservative scheduling and equip zone temperature sensors with timed override buttons. If a person wants to use a space when it hasn't been scheduled as unoccupied, they simply press the override button and the automation system switches that zone into the occupied mode. This returns the temperature to the occupied set point and delivers ventilation air to that zone. Typically, the zone automatically returns to the unoccupied mode after a certain period of time, 2 or 3 hours, for example. Using this timed override feature provides the opportunity to be more aggressive with scheduling. This avoids wasting energy by scheduling the unoccupied period based on typical usage, and allows the timed override feature to handle the worst case or once-a-year scenarios. Once occupants are educated about using timed override, energy savings and minimal complaints can coexist. Next, use separate time-of-day schedules for areas with differing usage patterns. For simplicity, many building managers define only one or a few time-of-day schedules to operate the entire building. However, if areas of the building have significantly different usage patterns, this approach wastes energy since the entire building may be operating to maintain occupied temperature set points, even though only part of the building is in use. Here's an example of a high school. For simplicity, all the classrooms are controlled by the same time-of-day schedule. The office area and the gym have their own schedules. A more energy-efficient approach may be to create more schedules for areas of the building with significantly different usage patterns. In this example, this wing of classrooms is used for after-school and evening activities, so it has a different schedule than the rest of the classrooms that are used only during school hours. Also, the auditorium and the auxiliary gym and the cafeteria each have their own schedules. If this facility already has a building automation system, it probably includes a time-of-day scheduling function, so the only additional cost is the operator's time to set up the schedules. Of course, you probably want to get carried away here. Find the proper balance. Group zones with similar usage patterns together and create one schedule for each group. Now, time-of-day operating schedules are often significant opportunities to save energy in existing buildings. Let's look at the results of 2 energy retrofit projects we've recently computed. The first example is a small school district located in Michigan. This project included implementing proper time-of-day scheduling and night setback in 3 school buildings. This chart shows the actual measured energy savings during the 4 years following implementation. In the first year, proper scheduling reduced energy use and saved $70,000. Although the amount of energy saved was fairly consistent over the next 3 years, a rate increase for natural gas at the beginning of the second year grew the utility cost savings to nearly $150,000. The second example is a government office building located in Florida. This project also included implementing time-of-day scheduling and night setback. In the first year, proper scheduling saved almost $15,000. Similar to the first example, a utility rate increase at the beginning of the second year grew the savings to $20,000. Now, through our energy retrofit projects, we've historically found more potential for energy saving through proper scheduling and night setback than from any other energy saving strategy.
All VAV systems save fan horsepower at part load by reducing airflow. That's one of the main reasons the industry embraced VAV systems in the 1980s. But high-performance VAV systems can save even more energy by using energy-efficient fan capacity control strategies. For us, that means fan pressure optimization. Of course, we've covered this topic in detail in other broadcasts, but it's still an important high-performance VAV strategy. In VAV systems, the damper in each box modulates to vary the primary air supplied to its zone to match cooling capacity to the cooling load. Varying zone damper position causes the pressure inside the supply ductwork to change. Traditional VAV air handling units modulate the supply fan to maintain the duct static pressure at a fixed set point. In many systems, the pressure sensor is located about 2/3 of the distance down the main supply duct with a static pressure set point of about 1 inch. Although it's traditionally recommended, there's nothing magical about that combination of distance and set point. It usually results in adequate static pressure for all zones at design conditions, and it assures that all boxes get adequate flow at part load conditions when all dampers are partly closed. The system maintains the static pressure at a fixed set point even though it's higher than would actually be needed to maintain adequate supply airflow to every zone. It's possible to optimize this static pressure control function to provide just enough pressure in the duct to satisfy the most wide open box. Reducing fan pressure reduces fan energy consumption, but it takes communicating controllers on the VAV boxes to do it. Each box controller knows the current position of its damper. The building automation system continually polls the box controllers, looking for the zone with the most open damper. The fan static pressure set point can be reset lower and lower until this particular VAV damper is nearly wide open. During this process, total supply airflow remains constant because the damper in each zone opens to maintain its required airflow, but the static pressure in the supply duct is reduced. The supply fan generates only enough static pressure to push the required quantity of air through the critical VAV box. The supply fan operates at a lower static pressure than it would with traditional control using a fixed 1-inch pressure set point. And as I mentioned, lower fan static pressure lowers fan horsepower and saves energy. But fan pressure optimization offers several other benefits too. First, it reduces the risk of fan surge. By allowing the fan to operate at lower pressures when the zone loads require less supply airflow, the fan operating point is always further away from the surge region than it would be using traditional duct pressure control. Second, lowering duct static pressure lowers sound levels. The supply fan doesn't need to generate as much static pressure at part load, so all VAV box dampers, even those close to the fan, will open more, resulting in lower air velocity and less noise generated at each box. And third, using fan pressure optimization with DDC controls allows the system to identify and ignore rogue zones where the thermostat cannot be satisfied even at design static pressure with the VAV damper wide open. Rogue zones prevent proper operation of duct static pressure control.
A rogue zone is one where something is not working properly. Maybe the VAV box was undersized, or there's a restriction in the duct that doesn't allow the required airflow. Maybe the zone temperature set point has been reset way too low. Or maybe the zone sensor was installed right above the coffee maker. Whatever the cause, with a conventional fixed duct pressure control, you would never know about these problems unless someone complained about comfort or noise. But with fan pressure optimization, the automation system regularly gathers data about each box, so it provides you with the opportunity to identify and fix these rogue zones. For example, here's a chart that trends the position of the VAV boxes in an actual building. In the morning, most of the boxes open up a little after 7 a.m. to warm up the building and warm up the zones. But the dampers are turned down quite a bit since not much cooling is needed. However, there is this one box, room 204, that's nearly wide open. This one box is preventing the duct pressure from being reset downward to reduce fan energy. This indicates that someone should go check that zone and fix the problem. Of course, it's not always possible to get to it right away. And what happens if we go fix that zone, and then we use the same trend a week later to see that we have a different rogue zone that was not apparent the first time because the first zone was overshadowing it. That's why it's helpful to have the building automation system be able to exclude any rogue zone from the control sequence. In this example, you would simply uncheck the box and remove 204 from the fan pressure optimization sequence. Now that box will still attempt to control space temperature, it just won't have a vote when determining the optimized duct pressure set point. Of course, this doesn't solve the comfort problem in that zone, but from the previous trend, we could see that this zone was starved for air anyway, so we would need to address it. During the first few months of operation, we could look at these kind of trends periodically, identifying any potential rogue zones, add them to our to-be-fixed list, and then exclude them from this sequence. After a while, we should have our list and notice that the system seems to be operating properly without one dominant or rogue zone. Then we send someone out to fix those problem zones, re-include them in the sequence, and then monitor the system to make sure they are no longer rogue.
Finally, fan pressure optimization allows for flexible sensor location. Because it uses the position of the VAV dampers to reset the static pressure set point, the sensor can be located almost anywhere in the supply ductwork. The most convenient location is usually near the outlet of the air handling unit. In some cases, the sensor can be factory installed and tested in the air handler and not relocated in the field. But it's usually better to mount it a few duct diameters away from the fan discharge, where turbulence is lower and static pressure is higher. When located near the fan outlet, the same sensor can also serve as a high pressure limit to help protect the ductwork from damage in the event of a fire damper closing.
Let's move on to supply air temperature reset. It's tempting to raise the supply air temperature at part load conditions in an attempt to save compressor or reheat energy. Increasing the supply air temperature reduces compressor energy because it allows the compressor to unload or cycle down. In addition, supply temperature reset increases the benefit of an air side economizer. When the outdoor air is cooler than the supply air set point, the compressors are shut off, and the outdoor and return air dampers modulate to deliver the desired supply air temperature. A warmer supply air temperature set point allows the compressors to be shut off sooner and increases the number of hours when the economizer provides free cooling. For those zones with very low cooling loads, where the supply airflow has been reduced to the minimum setting of the VAV box, raising the supply air temperature also decreases the use of reheat energy. However, because the supply air is warmer, those zones that require cooling will need more air to offset the cooling load. This increases fan energy. Finally, in climates with humid seasons, warmer supply air means less dehumidification at the coil and may result in higher humidity levels in the zones. So if dehumidification is a concern, use this strategy with caution. When used, this reset strategy should attempt to minimize overall system energy use. This requires considering the trade-off between compressor, reheat, and fan energy, while not ignoring space humidity levels. While there are many different approaches to implementing the strategy, papers and articles written on the subject tend to agree on some general principles for balancing these competing issues. First, as cooling loads begin to decrease, start by reducing supply airflow. This takes advantage of the significant energy savings from unloading the fan. In other words, when it's warm outside, keep the air cold so that you can reduce airflow first. Then begin to raise the supply air temperature when it can enhance the benefit of the air side economizer and reduce reheat energy. While there are several possible control schemes, I'm going to review 3 approaches today. The first approach is like fan pressure optimization that we just discussed. In this case, the position of the furthest open VAV damper is to reset both the duct pressure and the supply air temperature set point. Now, because fan energy savings is usually the biggest driver, this approach usually leads by reducing the duct pressure set point as low as possible, and then follows by raising the supply air temperature set point. That is, as zone cooling loads decrease and the boxes begin to close, the automation system keeps the supply air temperature cold and lowers the duct pressure set point to save fan energy. Then, once pressure has been reduced to the minimum limit, as the boxes continue to close, it begins to reset the supply air temperature upward. When zone cooling loads increase and boxes open back up, the automation system first lowers the supply temperature set point to design, then follows by increasing duct pressure. Now, a benefit of this approach is that it maximizes fan energy savings. since it waits until you've reset the duct pressure as low as possible before you raise the supply temperature set point. And it ensures comfort because no zone will overheat or be starved for air. A possible drawback is that in some applications, the supply air temperature may not get reset upward very often, so there might not be much reduction in reheat. Since this approach reduces duct pressure as much as possible first, the cooling load in every zone would need to be low enough that the duct pressure set point reaches the minimum limit and all the VAV dampers are still partially closed. Now, another common approach is to reset supply air temperature based on the changing outdoor temperature. When the outdoor dry bulb temperature is warm, higher than 65 degrees in this example, no reset takes place and the supply air set point remains at its designed value, 55 degrees in this case. Now, when it's warm outside, the outdoor air provides little or no cooling benefit for economizing. And the cooling load in most zones is likely high enough the reheat is not required to prevent overcooling. Out here, keeping the air cold allows the fan to turn down, taking advantage of the energy savings from reducing airflow. And the colder supply air temperature allows the system to provide sufficiently dry air to the zones, improving part load dehumidification. Then, when the outdoor temperature is cooler, the controls begin to reset the supply air temperature upward. At mild or cold outdoor temperatures, reset enhances the benefit of the economizer. And if there are any zone level reheat coils activated, it's reduced or even avoided reheat energy. Now, at these cooler temperatures, the supply fan has likely already unloaded significantly, so the incremental energy use of having to deliver a little more air is lessened. Finally, the amount of reset is capped at 60 degrees in this example. Now, limiting the amount of reset allows the system to satisfy cooling loads in interior zones without need to substantially oversize VAV terminal units and ductwork. This approach attempts to better balance fan energy savings and reheat energy savings. It still achieves a good amount of fan energy savings because it waits until it's cooler outside before raising the supply air temperature set point. But it doesn't wait for duct pressure to reach the minimum limit, so it may reduce reheat energy more than the first approach. A possible drawback is that when implemented in this open loop way that I showed, it doesn't have a way to ensure that a zone doesn't overheat. If there's a zone that requires colder air, even when it's cool outside, the warmer supply air may not provide enough cooling and that zone may get uncomfortable. The last approach I'll discuss today is basically a combination of the first two. The supply air temperature is reset based on outdoor temperature, but when reset takes place, the amount of reset depends on the cooling need of the worst case or critical zone. In this example chart, when it's 50 degrees outside, the system is going to try to reset the supply air temperature up to 60 degrees. However, if there's a zone that's at near design cooling load, that may not be cold enough. Using the current temperature and VAV damper position for that zone, the controls can determine that this much reset is just too much and either revert back to 55 degrees or lower the set point a degree or so and see if that solves the problem. Like with example 2, this approach attempts to better balance fan and reheat energy savings. But like example 1, it ensures comfort because no zone will overheat. One possible drawback is that it uses the same input signal, the position of the furthest open VAV damper, that is used for fan pressure optimization. So there needs to be some coordination of control sequences to ensure stable operation.
At part load, high humidity levels can become a concern in some zones regardless of climate. VAV systems don't need to be in New Orleans to have high humidity in some zones. Remember, when supply airflow drops in zones with low sensible heat ratios, relative humidity can rise considerably. To avoid high humidity in these zones, consider disabling supply temperature reset, either when it's very humid outdoors, like on a cool rainy day, or when the humidity in any of these zones exceeds a high limit, say 60 or 65%. The first approach requires an outdoor humidity sensor, while the second approach requires a humidity sensor in each of the low sensible heat ratio zones. And although a controller could be designed to reduce the supply air reset temperature incrementally as either outdoor or indoor humidity rises, it's probably less confusing for the operator if the BAS simply disables reset for the day and tries again tomorrow.
So, when considering using supply air temperature reset in a VAV system, first analyze the system to determine if the savings in compressor and reheat energy will outweigh the increase in fan energy. And as Dennis mentioned, don't ignore the impact on indoor humidity levels. For interior zones that may have near constant cooling loads during occupied periods, calculate design airflows for those zones based on the warmer reset supply air temperature. For our example, this would be 60 degrees rather than 55 degrees. While this may require larger VAV terminals and ductwork for those zones, it allows supply air reset to be used during mild weather and still provide the needed cooling for these weather-independent interior zones. Finally, design the air distribution system for low pressure losses and use the fan pressure optimization strategy to minimize the penalty of increased fan energy when the supply air temperature is raised.
A high-performance VAV system doesn't sacrifice occupant health and comfort for energy savings, but ventilation requirements are dynamic, so truly high-performance VAV systems use ventilation optimization or dynamic reset strategies to reduce intake airflow as system conditions change. The first of these is zone-level demand-controlled ventilation. Standard 62.1 recognizes that part-load outdoor airflow rates can be lower than design rates. It allows dynamic reset approaches for individual zones or for the entire ventilation system. Zone rates can be reset based on changes in zone population. We call these reset approaches demand-controlled ventilation. Several DCV approaches have been used to estimate current zone population, including time of day scheduling, occupancy sensors, and actual people counting methods such as ticket sales or turnstiles, or maybe even CO2-based calculations. Although this is possible, it requires sensing both zone and supply CO2 level along with supply airflow rate, and then solving a differential equation in real time. Most designers don't use this approach because it's complicated and prone to errors. Anyway, however it's established, estimated population can be used to find the breathing zone outdoor airflow rate currently required. But perhaps the most popular demand-controlled ventilation approach uses differential CO2 level to directly estimate the required outdoor airflow rate without first estimating population. This approach is described in the Standard 62 User's Manual. How does it work? It uses the steady-state concentration equation, shown here simply because we know engineers like equations. The rise in CO2 level in the zone depends on the CO2 generation rate per person and the outdoor airflow rate per person. Using this relationship, a simple proportional controller can be designed which uses the sensed differential CO2 level to estimate the outdoor airflow rate currently required for the zone. Again, the equation is shown here to be sure that we don't disappoint any engineers. But it's important to note that this approach estimates only the required outdoor airflow rate. It does not estimate the zone population, which is okay for many systems. All four zone-level demand-controlled ventilation approaches work fine when resetting outdoor air intake flow for single zone and 100% outdoor airflow systems, since the required zone outdoor airflow rate is all that's needed to find the intake airflow currently required. But multiple zone systems are a little different. Intake airflow must be based on changes in zone discharge airflow as well as changes in required zone outdoor airflow rate and changes in zone population. So multiple zone system equations, similar to those used during design must also be used to find outdoor air intake flow during operation. We call this dynamic reset approach ventilation reset control. In quick summary, it works like this. A typical VAV system is designed to bring in at least the minimum intake airflow required for proper ventilation of the critical zone. Remember, the critical ventilation zone needs the richest mixture of outdoor air in its primary airstream. In a properly designed system, all non-critical zones get excess outdoor air at design conditions. At any part load condition, if design intake airflow is maintained, all zones, including the critical zone, are overventilated. So Standard 62 permits the dynamic reset of outdoor air intake as operating conditions change without even considering population changes. Since each VAV controller knows its required outdoor airflow rate and senses zone discharge airflow, the BAS can collect this zone information and solve the multiple zone system equations to find the current intake airflow required. This becomes the new set point for outdoor air intake flow at the air handler, and that is how ventilation reset control works. But now returning to demand-controlled ventilation in multiple zone systems. The question arises, can zone-level demand-controlled ventilation be used to reset system intake airflow? The quick answer is yes, but how do you do it? Well, although any of the 4 zone-level approaches could be used in any zone, some designers want to install a CO2 sensor in every zone. The building automation system monitors each sensor and uses one of many approaches to determine how much outdoor air must be brought in at the air handler to satisfy the critical zone sensor, and then repositions the outdoor air damper accordingly. However, it's costly to use all these CO2 sensors. They must be high-quality sensors to reduce zone-to-zone sensing errors, which can lead to substantial underventilation or overventilation in the system. Besides, most zones in a VAV system are always somewhat overventilated and therefore never critical, regardless of operating conditions. Why should all non-critical zones bear the expense of installing and maintaining CO2 sensors if most of them don't help control the system anyway? Well, they probably shouldn't, not for control purposes anyway. In fact, any demand-controlled ventilation approach used at the zone level can be combined with ventilation reset control at the system level, in this way accounting for changes in zone population and changes in ventilation efficiency due to airflow. First, considering the zone level, CO2 sensors should be installed only in those zones that are densely occupied and experience widely varying population. In this example, this means CO2 sensors are only used in the conference room and the lounge. These are the best zones for CO2 sensing since they are most likely to become critical during operation. Less densely occupied zones, or those frequently unoccupied during normal operation, are probably better suited for occupancy sensors. Many zones in a typical office building fall into this category. In this example, each private office has an occupancy sensor to indicate whether it's occupied or not. When it's occupied, it needs design outdoor airflow, but when it's unoccupied, it requires considerably less. Finally, outdoor airflow for all other zones, those that are sparsely populated or occupied at a constant level or in a predictable pattern, is probably best determined using a time-of-day schedule in the building automation system. This schedule can simply indicate when a zone is expected to be occupied and ventilated for design population, or it can be used to vary the zone outdoor airflow requirements based on anticipated population level during each occupied hour. Of course, it's not always easy or even possible to accurately predict hourly population levels. Moving on to the system level, we again use ventilation reset control, but in this case, we also consider the changing outdoor airflow required in each zone. Just remember, High-performance VAV systems should use the most appropriate zone-level demand-controlled ventilation approach, whether it's time-of-day scheduling, occupancy sensing, population counting, or CO2 sensing, to find the current zone outdoor airflow rates. They should use ventilation reset control, where zone information is communicated to the BAS and where multiple zone calculations determine a new outdoor air intake flow set point to establish how much outdoor air must be introduced at the air handling unit at current operating conditions. And they should send this newly calculated set point to the air handler controller, which senses outdoor airflow and modulates the outdoor air damper to maintain this new set point. Designers use various calculation methods for multiple zone system reset, so ASHRAE is currently sponsoring research to compare several of these methods. This research was justified because it's clear that combining demand-controlled ventilation at the zone level with ventilation reset control at the system level has real value. It assures that each zone receives at least its minimum required outdoor air and that outdoor air intake flow is adjusted to the lowest allowable value, avoiding both IAQ problems due to underventilation and energy waste due to overventilation. Summarizing benefits, combining zone-level demand-controlled ventilation and system-level ventilation reset control can reduce outdoor air intake flow and save energy. And if CO2 sensors are used for demand-controlled ventilation, they are not required in every VAV zone. The CO2 sensors are really only needed in those potentially critical zones where they bring the most benefit. This minimizes installed cost and periodic calibration and cleaning needed to ensure proper sensor operation, and it avoids the risk of over or under ventilation due to faulty sensor readings. For most zones, occupancy sensors and time-of-day schedules can be used effectively to reset zone ventilation requirements.
Dennis, you mentioned that in some zones, an occupancy sensor is a good technology for demand control ventilation. That sensor indicates if the zone is actually unoccupied, even though the automation system has scheduled it as normally occupied. We call this occupied standby mode. While this signal can be used to reduce ventilation, let's not stop there. In this occupied standby mode, all or some of the lights in that zone can be shut off. The temperature set points can be raised or lowered by 1 or 2 degrees, and the minimum required outdoor airflow for that zone can be reduced. The purpose of each of these actions is to save energy. Here's an example conference room. When occupied, this zone requires 310 CFM of outdoor air, which is 5 CFM per person plus 0.06 CFM per square foot of floor area. During the occupied standby mode, when nobody's actually in the room, the ventilation can be reduced to just the base ventilation rate of 0.06 CFM per square foot, or 60 CFM in this example. In addition, the minimum primary airflow setting of the VAV terminal is related to ventilation. Of course, this setting should be higher than the outdoor airflow requirement, so the outdoor air fraction doesn't reach 100%. In this example, when occupied, the minimum primary airflow setting for this zone is 450 CFM, so its worst case OA fraction would be 70%. During the occupied standby mode, when the outdoor airflow drops from 310 to 60 CFM, we can often lower this minimum primary airflow setting as well. In this example, the minimum primary airflow setting is reduced from 450 CFM to 225 CFM when nobody is in the zone. This reduces or avoids the need for reheat and saves fan energy.
A high-performance VAV system senses outdoor airflow and resets it to match current conditions, so it needs outdoor airflow sensing. Many indirect and direct methods have been used to sense outdoor airflow. For instance, Trane developed a combination damper and airflow sensor many years ago specifically for outdoor airflow measurement and control. It's called Traq Damper, and it's not new to most of you, but I want to talk about it to illustrate some of the challenges of outdoor airflow sensing. It consists of opposed blade dampers mounted in a round bell mouth housing, a differential pressure sensing ring at the inlet, and an electronic signal processing module. The accuracy and reliability of differential pressure sensing to determine airflow has been proven by years of use in VAV boxes from various manufacturers. However, due to the very low differential pressure signal produced at minimum outdoor airflow, a high-tech signal processing transducer, not a general-purpose pressure transducer, is required. And the low pressure signal is sensitive to changes in air density, so the transducer senses temperature and recalibrates every minute to correct for density changes. To reduce inaccuracy due to air turbulence, as well as to reduce overall pressure drop, a bell mouth intake is used. Similar to other damper and sensor combinations, the result of all these design features is a very accurate airflow sensor over a very wide range of airflow values. Certified as an airflow measurement station according to AMCA 610 requirements, this damper assembly can measure outdoor airflow to within plus or minus 5% of the actual rate over a range from full design airflow all the way down to 15% of design airflow. And using sequence damper configurations, that range can be extended down to 5% of design airflow. It's a low leak damper that meets standard 90.1 and 189.1 damper leakage requirements too. Some designers think that airflow measuring devices based on pressure inherently add too much pressure drop at design airflow compared to straight blade dampers. Well, a device like the Traq Damper assembly does have a little higher wide open pressure drop than a blade damper alone. For example, in a size 25 air handler delivering 12,500 CFM, this round damper assembly has a 0.3-inch pressure drop compared to a straight blade damper with a 0.25-inch pressure drop. But the sensor in the round damper assembly doesn't need an upstream filter, while most airflow monitoring stations do need upstream filtration for reliable sensing. If a MERV 8 filter is used upstream of the damper in our example, the pressure drop for the complete assembly increases to 0.64 inches. So be sure to account for all pressure drops when comparing outdoor airflow sensing and control approaches.
Of course, the impact of these control strategies depend on climate, building use, and utility costs. To illustrate, we use Trace 700 to model an office building and compare a typical VAV system to a system that uses several of these optimized control strategies that we just discussed. These results show that there is potential to save a significant amount of energy in a VAV system just by controlling it in a more optimal way. The blue column to the left for each city is the typical system, and the green column to the right is a system with optimized controls. The y-axis is overall HVAC energy use, shown as a percentage of the base case. Just optimizing how the system is controlled reduced HVAC energy use by 9% for the building in Houston, 11% in Los Angeles, 17% in Philadelphia, and 18% in St. Louis.
While they're a very important part of high-performance VAV systems, these optimized system control strategies can be used on any VAV system. Another key ingredient of many high-performance VAV systems, especially chilled water VAV, is low-temperature air.
Supplying air at a colder temperature allows the system to deliver a lower airflow rate. This can significantly reduce fan energy use. It can also allow fans, air handlers, and VAV terminals to be downsized, which reduces installed cost. Sometimes ductwork is downsized also, which further reduces installed cost. Another benefit is that delivering colder air means that the air is drier, which can lower indoor humidity levels in climates with humid seasons. While supplying air at a colder temperature reduces fan energy use, it can increase reheat energy use and result in fewer hours when the airside economizer can provide all the necessary cooling. These impacts partially offset the fan energy savings. Therefore, intelligent system control is crucial to fully realize the potential energy savings of a low-temperature VAV system. So here are some tips for maximizing energy savings with this approach. First, as I explained earlier, resetting the supply air temperature upward during mild weather helps to maximize the benefit of the airside economizer and reduces reheat energy use. To explain, let's look closer at the impact of colder supply air on reheat energy. Here's a VAV box used in a conventional 55-degree system. Design primary airflow for this zone is 1000 CFM, and the minimum primary airflow setting is 300 CFM, or 30% of design. Now, as the sensible cooling load in the zone decreases, the damper in the VAV box modulates to reduce primary airflow delivered. When primary airflow reaches this minimum setting and the cooling load continues to decrease, the heating coil warms the air to avoid overcooling the zone. For this example, the reheat coil will be activated when the space-sensible cooling load drops below 30% of design. Now let's look at the same zone, but for a cold air 48-degree system. Design primary airflow is reduced to 740 CFM. The minimum primary airflow setting in terms of CFM is unchanged. It's still 300 CFM. This is because the minimum setting is to ensure proper ventilation or to ensure proper operation of the supplier diffusers. Both are based on actual CFM, not on some arbitrary percentage. While the minimum CFM is the same, the percentage is higher, 40% rather than 30%. What this means is that for this example, the reheat coil would be activated when the space-sensible cooling load drops below 40% of design, which means it will activate sooner than a conventional 55-degree system.
For a comfort cooling application, 90.1 limits the energy used to reheat air that has been previously cooled. One of the prescriptive limits allows the use of new energy for reheat if the zone airflow is first reduced to 30% of design airflow. However, a higher percentage can be used as long as it results in less overall energy use. Or, if recovered heat is used for reheat, this percentage can be as high as you want. We did a broadcast on this back in 2008 if you want to get into the details.
Let's look at this another way, so we see the whole picture. Again, here's the VAV box used in a 55-degree system. As the sensible cooling load in the zone decreases, the damper reduces primary airflow from 1000 CFM at design to 300 CFM at minimum. When primary airflow reaches minimum and the space load continues to decrease, the reheat coil adds heat to raise supplier temperature and avoids overcooling the zone. Now, here's the VAV box in the cold air system. This box reduces primary airflow from 740 CFM at design to 300 CFM at minimum. Here you can see that the reheat coil is activated sooner. Now this red triangle depicts the heat added by the reheat coil in the cold air system. The orange triangle depicts the heat added for the conventional system. So the additional reheat energy for the cold air system is this section down here. The additional heat needed to warm the air from 48 degrees up to 55 degrees. Now for the rest of the picture. First, don't forget that while reheat energy increases, there's a large reduction in fan energy use over here. And if you use supplier temperature reset to raise supply air from 48 back up to 55 degrees, this difference in here gets a lot smaller and maybe even goes away. So intelligent use of supplier temperature reset is crucial to fully realize the potential energy savings with cold air. The second tip, since ASHRAE standard 55 shows that people are comfortable at warmer temperatures when humidity is lower, the lower humidity levels that occur with cold air systems provide the opportunity to raise the space temperature set point by 1 or 2 degrees. This further reduces airflow and fan energy use, and reduces cooling energy a little too. Now I suggest starting conservative and try raising the set point by just 1 degree. We know of schools in Florida, however, that have cold air VAV systems where the thermostats are set 2 or 3 degrees higher than other school buildings in the district. Next, while I did say that lowering the supplier temperature can allow you to downsize ducts to reduce first cost, if you want to maximize energy savings, consider designing the system for colder air, but keep ductwork the same size as it would be for 55-degree supply air. This further reduces fan energy and allows supplier temperature reset to be used in systems without concern for any zones with near constant cooling loads. Keeping the same size ducts also improves the ability of the system to respond to any future increases in loads, since it will be capable of handling an increased airflow rate if needed. To demonstrate the benefits of these strategies, here are the results of a trace analysis for an example office building. First, let's see what happens when we downsize the ducts as much as possible to reduce the installed cost. In this example, designing the VAV system for 48-degree supply air rather than 55 degrees saves a little bit of energy to go along with a big installed cost reduction. If you raise the space temperature set point by 1 degree, this further reduces airflow and results in even more energy savings and even more installed cost savings. But what if we want to maximize energy savings and keep the ductwork the same size? These last 3 columns show the same building without downsizing the ducts. This results in even lower overall system energy use. Again, raising space temperature set point by just 1 degree and then resetting supplier temperature upward during mild weather both result in even less energy use. To wrap up the discussion of duct sizing, there is a way to get this energy savings and still reduce ductwork installed cost. Round ductwork allows you to design for higher velocities and allows for the use of the static regain duct design method. Combined, this can significantly reduce the amount of sheet metal, often saving $1 to $1.50 per square foot. The final tip is to consider using parallel fan-powered VAV terminals in the perimeter zones and maybe some interior zones that experience wide variations in cooling load. This type of terminal activates a small fan to draw warm air from the ceiling plenum as the first stage of heating. Heat generated by the light fixtures, which warm the air in the plenum, is recovered to reduce reheat energy use.
Of course, cold air systems are not without challenges. Design engineers typically express 2 concerns with this approach. First, minimizing comfort issues related to cold air dumping on the occupants. And second, avoiding condensation on components in the air distribution system. A great resource for anyone designing a cold air system is this ASHRAE Cold Air Distribution Design Guide. It discusses how to avoid these problems in detail. And Trane recently published a new application manual on chilled water VAV systems that also discusses low temperature air. Nobody wants cold air dumping on their neck. That's why linear slot diffusers with high induction ratio are good for any VAV system, but really great for these cold air systems. They induce large quantities of air from the space to mix with the cold supply air so that the mixture drops slowly into the occupied zone at nearly room temperature. On the other hand, conventional low induction diffusers allow cold air to drop directly into the occupied zone, which can result in cold air dumping and occupant comfort complaints, especially at reduced airflows. Another approach to avoid dumping is to use either series or parallel fan-powered VAV terminal units to blend warm plenum air with cold primary air before it gets to the diffusers. In this example, the terminal unit uses its continuously operating fan to mix 80-degree air from the plenum with 45-degree primary air, so the diffusers discharge air at 55 degrees. This approach allows you to use low-cost diffusers with lower induction ratios, but remember, these terminal units add first cost and the unit fans consume energy continuously whenever the zone is occupied. The other issue is condensation. Since the surfaces of the air distribution components in a low-temperature system are colder than in a conventional system, everyone worries about condensation on the diffusers or ductwork. So how do you avoid it? First, insulate all the cold surfaces. This includes supply ducts, VAV terminals, and diffusers. You should be doing this anyway to avoid wasting energy and to comply with Standard 62, but it's vital in a cold air system. Of course, insulation alone cannot prevent condensation. A properly sealed vapor retarder must be included on the warm side of the insulation to prevent condensation within the insulation itself. Let me share some of our experience here. The Trane district office in Dallas has used the low temperature VAV system for many years. It delivers 44-degree air to the zones through linear slot diffusers. Here's a photo from above the ceiling. Engineers in that office got up on a ladder and used an infrared device to measure the outside surface temperature of the duct insulation. At the time, the system was delivering 44-degree supply air and it was 85 degrees in the plenum. The main supply duct had 2 inches of insulation with a surface temperature of 82 degrees. The branch duct had only 1 inch of insulation with a surface temperature of 77 degrees. Both of these surface temperatures were well above the dew point in the plenum, which incidentally was pretty low. The average relative humidity in the building is only 39% during summer operation. And I hope you can see this. There's a nice even layer of dust covering the ducts. This is a telltale sign that condensation has not occurred. If it had, you would see streaks in the dust where the condensation dripped off the insulation. Part of this building is a warehouse with a very tall plenum, so a fully ducted return air path was used. But low temperature supply air can be used successfully with either a plenum return or a ducted return, as long as the plenum is sealed properly from outdoors. If possible though, use an open sealing plenum for all VAV system return. This results in a conditioned plenum, which means a lower dew point and even less risk of condensation and better building air distribution at all load conditions. Let's review some best practices. First, insulate. Use a return plenum if possible. During humid weather, maintain positive building pressure to reduce or eliminate the infiltration of humid outdoor air. Using a high induction linear slot diffuser also avoids condensation on the room side of diffusers. Monitor indoor humidity during unoccupied periods and turn on the system as necessary to prevent humidity from rising too high. This might mean turning on the cooling system to reduce dew point or simply turning on the fan to mix the air in the building. And very important, during startup, slowly ramp the supply air temperature downward to slowly lower surface temperatures while lowering dew point in the building. If you start up with a very low supply temperature, it's a race. Some surfaces cool below the falling building dew point temperature, causing local condensation. You want all condensation to occur at the cooling coil while pulling down the building dew point, so reduce supply air temperature gradually. Here are 2 example pull-down sequences. One approach simply resets the supply air temperature lower and lower based on the time of day schedule. Rather than starting up the system and immediately delivering 48-degree air, the system starts up delivering 55-degree air, then steps down to 48 degrees gradually. Another approach uses an indoor dew point sensor and ramps down the supply air temperature based on how quickly the indoor dew point decreases. These and other recommendations for preventing condensation are discussed in the design guide and the Trane application manual mentioned earlier and listed in the bibliography.
Cold air VAV systems can be an important part of high-performance VAV systems, reducing energy use and improving occupant comfort. Next, as Dennis mentioned earlier, air-to-air energy recovery is likely to be a part of many high-performance buildings going forward, including those that use VAV systems.
Air-to-air energy recovery refers to the transfer of sensible heat or sensible heat and moisture between two airstreams. In a VAV system, the most common use is to precondition outdoor air as it enters the building for ventilation. An air-to-air heat exchanger is arranged to exchange energy between the outdoor and the exhaust air streams. When it's hot and humid outside, this device transfers energy from the outdoor air to the cooler, drier exhaust air stream. When it's cold outside, it transfers heat from the warmer exhaust air leaving the building to the cold air entering. Sensible energy recovery devices transfer only sensible heat. Total energy recovery devices transfer not only sensible heat, but also moisture. Now, using air-to-air energy recovery offers the following benefits. It reduces cooling and heating energy, and when total energy recovery is used, it also reduces dehumidification and humidification energy. Plus, it can allow for downsizing of the cooling and heating equipment. However, there are some drawbacks that need to be justified. First, the wheel adds pressure drop, which increases fan energy. And routing the exhaust air back to the device may require more ductwork and sealing space than a system without energy recovery. When using energy recovery to precondition outdoor air in a VAV system, consider these recommendations. First, properly size the energy recovery device. In a mixed air VAV system, size the device to precondition only the minimum outdoor airflow required for ventilation, not the maximum airflow expected during economizer operation. Second, strive for balanced airflows. Duct as much exhaust air back to the energy recovery device as possible, including restroom exhaust, for instance. The less disparity between outdoor and exhaust airflows, the more energy can be recovered. Third, achieving maximum energy savings depends on proper control of the energy recovery device within the system. To demonstrate, this chart shows annual weather conditions for Miami, looking only at daytime hours. Even in a hot climate like this, there are 560 hours when the enthalpy of the entering outdoor air is lower than the enthalpy of the return air, or exhaust air, leaving the building. At these times, a total energy wheel should be turned off to avoid wasting energy. If left on continuously, it would actually increase the cooling load by transferring unwanted heat to the entering outdoor air. Now, this chart is for St. Louis, a less cooling dominated climate than Miami. In this case, there are almost 1,500 hours when a total energy wheel should be turned off to avoid wasting energy. Of course, since this climate experiences some cold weather too, the wheel is turned on again when heating is needed. And speaking of heating, in a VAV system, you may also need some means to modulate the capacity of the energy recovery device to avoid overheating the air. This schematic depicts a VAV system operating when it's 30 degrees outside. If the wheel is turned on and operates at full capacity, it would transfer heat from the warm exhaust air, preheating the entering outdoor air, in this case to about 63 degrees. When this air mixes with the recirculated return air, the resulting mixed air temperature is 66 degrees. And the cooling coil needs to operate in order to cool the supply air to the desired 55 degrees. Alternatively, if the wheel is turned off to avoid overheating, the 30-degree outdoor air results in a mixed air temperature of 48, and the heating equipment would need to operate. So in a VAV system, some means for modulating capacity of the energy recovery device is needed. In the case of a wheel, as shown here, we recommend modulating the exhaust side bypass damper to vary its capacity and avoid overheating the supply air. The bypass damper reduces the amount of air flowing through the exhaust side of this side of the wheel, which results in less heat recovered, and the wheel heats the entering outdoor air to only 43 degrees. The resulting mixed air temperature is 55 degrees, so no mechanical cooling or no mechanical heating is required. So proper control is very important. Turn the device off during mild weather to avoid wasting energy, and modulate its capacity during cold weather to avoid overheating. In many climates, an airside economizer can provide the benefits of free cooling for much of the year. When the economizer is activated, the outdoor air is at the right temperature to provide cooling, so the energy recovery device offers no benefit and should be turned off. In a mixed air system, bypass dampers should be included to avoid higher pressure drop when outdoor airflow is increased for economizing. Finally, in cold climates, provide some means for frost prevention. When it's very cold outside, the surface temperature can drop below the dew point of the exhaust air. The water vapor will condense and freeze, eventually blocking airflow. There are various approaches to frost prevention. The choice depends on the number of hours that frost might be expected to occur.
Most of our discussion today has focused on the air side of VAV systems. Of course, there are also many opportunities to reduce energy on the equipment side of the system. For a rooftop VAV system, high-efficiency rooftop equipment, in some cases equipped with an evaporative condenser, should be considered. An evaporative condenser sprays water over the outer surfaces of the condenser tubes, lowering the refrigerant condensing temperature and improving compressor efficiency. In some applications, a central relief fan rather than a return fan can result in less system energy use, since the relief fan can often be turned off during non-economizing hours. Finally, some buildings may find that using solar collector panels can be a very effective way of providing hot water for reheat. And for those VAV systems that use chilled water, strategies like low flow, low temperature systems and ice storage match up very well with lowering supply air temperature. And variable water flow, high efficiency chillers or boilers, optimized plant controls, and water side heat recovery should all be considered. Finally, last spring we produced an ENL broadcast to discuss using geothermal with central plants.
We've shared several strategies today for making a VAV system high performance. But the impact of any of these strategies on overall operating costs depends on climate, building use, and utility costs. As an example, we use Trace to model an office building and compare a typical VAV system to a high-performance chilled water VAV system. The high-performance system uses 48-degree supply air rather than the conventional 55, but the ductwork has not been downsized. It also uses the optimized VAV control strategies, parallel fan-powered VAV terminals, and a low-flow, low-temperature, water-cooled chiller plant. The baseline building uses a conventional chilled water VAV system with 55-degree supply air and modeled according to Appendix G of Trane 90.1. For this example, the building with a high-performance chilled water VAV system uses about 20% less energy than the baseline VAV system in either Houston, Philadelphia, or St. Louis. The building uses about 10% less in Los Angeles, which has milder weather and lots of hours for airside economizing. As a comparison, this is also 5 to 10% better than an active chilled beam system that was modeled for this same building. Now we use Trace to also model a smaller office building that uses a high-performance rooftop VAV system. This system uses 52-degree supply air, optimized VAV controls, parallel fan-power VAV terminals, and a high-efficiency rooftop unit. You'll note that the supply air temperature is not as cold as in the chilled water VAV system. The optimal supply air temperature will vary for different system configurations and climates. It will likely be higher for an air-cooled DX system than for a water-cooled chiller system. The baseline building uses a conventional rooftop VAV system, again modeled according to Appendix G. For this example, the building with a high-performance rooftop VAV system uses nearly 20% less energy than the baseline system in either Houston, Philadelphia, or St. Louis, and about 12% less in Los Angeles. As a comparison, this is also 5 to 12% better than a variable refrigerant flow system that was modeled in this same building. Finally, some of you may be familiar with a series of advanced energy design guides that are funded by the U.S. Department of Energy and have been jointly developed by ASHRAE, the American Institute of Architects, the Illuminating Engineering Society, and the U.S. Green Building Council. These guides include a series of climate-specific recommendations that can be used to achieve 30%, or in some cases 50%, energy savings over a conventional design. For each climate zone, there's a table that lists the prescriptive recommendations. There are currently 7 guides in the series, each for a different type of building, from office buildings to schools to warehouses. Electronic versions of these guides are available for free download at the website shown on the slide. The Department of Energy used Energy Plus to perform whole building energy simulations to verify that these recommendations achieve the stated energy reduction. These simulations consider the interaction of the various subsystems, including the building envelope, lighting, HVAC, and surface water heating. Most of these guides include several options for HVAC systems, and several of them include VAV systems as one of the options that can help the overall building achieve the energy saving threshold. In the recently published guide for small and medium-sized office buildings, a high-performance rooftop VAV system is included as one of the options that can be used to achieve 50% energy savings. In the guides for K-12 school buildings and small healthcare facilities, both rooftop VAV and chiller boiler VAV systems are included as one of the options for achieving 30% energy savings. These guides, which were funded by the U.S. Department of Energy, published by ASHRAE, and developed by representatives from the associations I mentioned, provide third-party validation that VAV systems can be used in high-performance buildings. Well, Jeannie, that brings us to the end of today's presentation.
Today, we discussed several strategies for making a VAV system high performance. Any VAV system can make use of optimized system controls like fan pressure optimization and ventilation optimization. And low temperature air can be valuable in a lot of VAV systems, especially chilled water VAV systems. Finally, strategies like air-to-air energy recovery, evaporative condensing on a rooftop unit, a low-flow chilled water system, or central geothermal can make a system truly high performance. Our example energy models and the advanced energy design guides help validate that VAV systems can be used in high performance buildings. Now, there are a number of publications available that provide more information on the material covered today, including several engineers' newsletters, application manuals, numerous articles, and a recently released engineers' newsletter. A bibliography detailing these resources is available from your local site coordinator. Additionally, past broadcasts are available to order on trane.com/ENL. And we've also have USGBC approved lead continuing education courses available on demand free of charge. Visit trane.com/continuing education for a complete list of courses available. And please remember to fill out a survey and let us know how we're doing. AIA members, remember to turn in your member information to your local site coordinator. Now, we have one more engineers newsletter this year, so please plan to join your local Trane office in October when we'll discuss dedicated outdoor air units. Thanks for joining us today. Have a fantastic summer.